and those are the red particles being emitted. You might wonder, why are they rising up? Aren't they supposed to be blasted right at the neighbors' faces? Well, not quite, because actually warm air tends to rise. So we're going to come back to that later in this talk, but the air around you does tend to rise, and especially if masks are worn, which really prevents the momentum of the fluid to be imparted by the breath, you will tend to see it rise, and then it actually becomes mixed by the natural air currents in the room. And as shown in this simulation, if you compare with people sitting at 1 meter or 6 feet or further, there's almost no dependence on distance in the ultimate sort of inhalation over time of those particles by people that are at least some distance away. So let's just take 1 meter as a somewhat arbitrary number. So that's at least some evidence that these kinds of models are useful. I should mention that in the field of building engineering and also indoor health of buildings, the concept of a well-mixed room is a starting point for all modeling that goes back many decades, not only for disease, but for other types of calculations, for example, of the energy cost to optimize ventilation systems for humidity and temperature, et cetera. So it's a reasonably well-validated concept, not to say that there aren't departures from well-mixedness, as we see in this simulation even, but certainly it's a good starting point. And if you want a universal guideline, I would argue it's actually really the only starting point, frankly, because you would need to otherwise know some details of each specific case. Again, for this audience, this may not be necessary, but let me go over the production of droplets from respiration and knowing that